Now we're going to look at capacitors and dielectrics that go in between the capacitors. And if you remember from the last video that a capacitor is just two parallel plates that store electricity. You charge up those plates and it'll hold on to the electricity until you need to use it elsewhere. A capacitor holds charge and then releases it when needed. It's used in circuits for timing devices. It's used for all sorts of applications. It acts like a storage area for electric energy. It's not a battery because that uses a chemical reaction. This simply just holds the charge. So the equations we have here are an electric field between those parallel plate capacitors is the change in voltage divided by the distance between the plates. And the new equation is the capacitance equals the charge per voltage per potential difference on the plates. So C is capacitance measured in farads, F. Q is charge on the plate measured in coulombs. Delta V is the potential difference between the plates measured in volts. D is the distance between plates measured in meters. And E is the electric field measured in newtons per coulomb. Here's another application for a capacitor. Here's our two parallel plates. And this is a transistor switch. And this is the data line coming in, and this is an address line. So a transistor-capacitor combination is part of a RAM chip used in computer memories. This capacitor fills up and releases charge, fills up and releases charge in this circuit. Here's a capacitor with a dielectric, which is a material between the capacitor that keeps the plates separate. Sometime we've been talking about capacitors as having a vacuum or an empty space in between the two plates. But a lot of times you'll have like paper or cardboard or some kind of insulator in between the two plates so electricity cannot go across the two, cannot go from one to the other. It's an insulator of some kind to hold the charge. Here's our other equation. C equals kappa times epsilon naught times the area of the plates divided by D. Now C is the capacitance measured in farads. Kappa is a dielectric constant. It's different for different materials. Paper is different than cardboard, etc., and then styrofoam, etc. Epsilon naught is called the permittivity constant, and it has a value of 8.85 times 10 to the negative 12. And the units are coulomb squared per newton meter squared. This is just a constant. It's always this value, epsilon naught. So our equation here has the kappa for the dielectric constant, the epsilon naught is the permittivity constant, the A is the area of the plates, that's in meters squared, and D is that distance between the two plates. Now this question will come up, and when you're asked if you want to change the value of a capacitor, this is the equation you have to use. It's capital, you either change the area of the plates or the distance between the plates. You cannot use that equation we just looked at, C equals Q over V, because whether you change the charge on the plates or the potential difference between the plates does not change the capacitance of the plate at all. You have to either change the dielectric constant in between the plates, you have to change the area of the plates or the distance between the plates. That's the only way to change a capacitor. There's different dielectric constants that can be found. Vacuum is 1, air is 1.00054, Teflon is 2.1, ruby mica is 5.4, and there's all sorts of charts out there that'll give you dielectric constants. An interesting application of a capacitor is when you push down on the key, on a keyboard key, the capacitance changes so the charge will flow away from the plates. The computer can sense which key is pushed this way. So this is just a capacitor. This is a movable plate that'll move up and down. And because you're changing the distance between the plates, you're changing the capacitance. Therefore, charge flows, and the computer can sense where charge is flowing from, and it'll know if it's a B or whatever, etc. There's all sorts of applications like this. Changing the distance between plates to have charge flow into or out of the plate is very common use of a capacitor. You'll also go ahead and find the energy stored in the capacitor. 1/2 Q times V is the potential energy in the capacitor. And you can also take this equation, capacitance equals Q over V, and do variations. Combine these two equations and come up with two other equations for potential energy of a capacitor. The other one was 1/2 CV squared, and then the third one is 1/2 Q over C. So there is two other equations that you can come up with, and see if you can come up with those on your own.